Laplacian generalizes the second derivative. But what does the second derivative measures? For the motivation, let's look at the finite difference approximation. Consider, for instance, the discretization with the mesh size 1, so that the derivative at x is f of x plus 1 minus f of x divided by the mesh size, so divided by 1. Then the second derivative is approximately the first derivative at x minus the first derivative at the previous point. So it is the difference of two differences. And when we simplify, we get fx plus 1 plus fx minus 1 minus 2fx. And pulling 2 out, we get this expression. So essentially, the second derivative is a constant multiplied by the difference between the average at two neighboring points minus f of x. So how do you interpret this expression? Constant multiplied by the average at neighbors minus f of x. So here's x, these are neighbors. So we look at the y values of the neighbors, we take their average, and we subtract the y value exactly at x. So this distance, this difference between the average and at the neighbors and the y value at x, it measures how different our function is from the straight line. So if this gap is positive, then the function is concave upwards. And if the difference between the average and f of x is negative, intuitively that means that the function is concave downwards. On the two-dimensional lattice, we can define a discrete Laplacian similar to how we defined, how we discussed discrete version of the second derivative. So at a given point, we measure the difference between the average value of our function at the neighbors minus the value of our function at the given point. So in this example, for instance, suppose the temperature at the given point is 45 degrees and at the neighbors is like here, 40, 50, 60, and 70 degrees. So we take the average of the neighbors and subtract the 45, so we get 10 degrees. So the average of the neighbors is 10 degrees hotter than the temperature at this point. An immediate consequence of this is the mean value theorem, that if the discrete Laplacian is 0 at some point, that means that the value of our function at that point is the average of the values of that function at the neighbors. The continuous case is similar. The value of u at the point is the average of the values of u at a circle centered at that point. Another application of Laplacian comes from physics. Laplacian is the divergence of the gradient of function u. As an example, suppose that u is x squared minus y squared. For instance, it can represent temperature on the plane. So here we have level curves of the temperature function. So for instance, when temperature equal to 0, it's either when x equal to y or when x equal to minus y. And when the temperature is equal to 1, that is this curve, also this curve, etc. Now the gradient is a vector, so at each point xy there is a vector with coordinates 2x and minus 2y. It's we can represent it with an arrow. So the arrow is directed towards the fastest increase of the temperature at that point, in the direction of the fastest increase. And the value, the length of that arrow, which is the absolute value, the length of the gradient vector, it represents the directional derivative of u in the direction of the fastest increase of the temperature. Now let's compute the Laplacian of u. So it is the divergence of the gradient vector field. So we take the x component of the gradient vector field and we differentiate it with respect to x. And then we add the derivative of the y component of that vector field with respect to y. So we have 2 minus 2, which is 0. So the Laplacian of this function is 0. Functions like this are called harmonic. So as we've seen, 0 Laplacian intuitively means that the temperature at each point is the average of the values of the neighbors. And here is a graph of this function u. The gradient field of this function can model the flow of heat, or more specifically, the heat flows in the opposite direction of the gradient. The heat flows from higher temperature to lower temperature. So it goes in the opposite direction of these arrows. And we can also visualize what it means for the Laplacian to be 0, or more specifically for the divergence of the gradient field to be 0. That means that there are no sources of cold and heat inside of the region. So whatever heat is flowing in, it will be flowing out. How does change of basis affect the gradient, divergence, and Laplacian? First of all, the gradient and divergence can be defined entirely coordinate free. For example, the gradient, it points in the direction where the function u grows the fastest, as we discussed. And the length of that vector, of the gradient vector, it's simply the rate of change of u in that direction. We can also define divergence coordinate free. So we would say, okay, suppose we have some vector field. So at every point xy we have a vector. Then the divergence of that vector field at point xy is simply the limit of the we consider disks centered at the point xy, and let's denote by this absolute value of d the area of the disk. So we are computing the flux of the vector field outside of the boundary of the disk. So we have this flux integral divided by the area of the disk, and we take the limit as the area of the disk goes to 0. Okay, So if this limit exists, so that it will give us the divergence. So that's coordinate-free definition of divergence. Now, in this definition, it doesn't have to be a disk. It can be any. So it can be any region enclosed in a loop. Okay, and as long as the area of that region goes to 0, the quotient of the flux of the vector field outside of the region divided by the area of the region. So the limit of this quotient approaches divergence of the vector. Now this definition it assumes that we have a way to measure distances on the plane. For instance, when we measure the rate of change, we need to be able to measure distance between 2 points on the plane. And it also assumes that we know how to compute inner product between two vectors. There is a second definition that works in any orthonormal basis. So if our vector field has components P and Q with respect to some orthonormal basis ij, then the divergence of the vector field is simply the sum of two partial derivatives. The partial derivative of P with respect to the first variable plus partial derivative of Q with respect to the second variable. The equivalence of these definitions is proved in calculus. Let's show the rotational invariance of gradient and divergence using an example. Okay, so we start with the standard basis ij, and let's apply a rotation to it. So we look at the new basis given by columns 3, 5, 4, 5 and minus 4, 5, 3, 5. These two columns are orthogonal and the two vectors have length 1. So the corresponding transformation is actually given by orthogonal matrix. A transpose A is identity. So let's try to find the gradient and divergence in the new coordinates. First observe that if we have a vector given in the new coordinates, we can easily find the old coordinates. Because we know the old coordinates of the new basis vectors, they are given. So we just replace the new coordinates by their expressions in terms of the old basis. So we get so coordinates of v, x, y, they would be given by these formulas. Okay. You can also write it in the matrix form. So xy would be our transformation matrix multiplied by the column x prime, y prime. Now, given a function on a plane, we can think about it as a function of x prime, y prime, and we compute the derivatives with respect to x, y prime, y prime using the chain rule. Now, the partial derivatives dx, dx prime, that's simply, okay, so this partial derivative is simply 3 over 5. Similarly, the partial derivative dy dx prime is this 4 over 5. And similarly for the other two partial derivatives. So we obtain the formula how to change from partial derivatives with respect to xy to partial derivatives with respect to x prime, y prime. We simply need to take our transformation matrix and multiply the vector of derivatives with respect to the old variables by the transpose of our transformation matrix to get the partial derivatives of u with respect to new variables. Then the gradient of u, so in terms of the new basis, it's just a vector of new partial derivatives, okay? And since the new basis we know how to express in terms of the old basis, so we write this linear combination in matrix form. So we place these columns into matrix A, multiplied by the vector of the new partial derivatives, the weights, okay? Now, the vector of the new partial derivatives is A transpose times the vector of the old partial derivatives. So we plug it in. Okay, so we are getting A times A transpose times ux uy. Now A times A transpose is the identity matrix because our transformation is a rotation, so A is orthogonal matrix, as we discussed, okay? So the final result is that our gradient vector is simply our gradient vector in terms of the new coordinates is the same as gradient vector in terms of the old coordinates. Okay, so that's how it works. Now, finally, let's move to the Laplacian. So, when we changed the basis using orthogonal transformation, like rotation, our gradient would have a similar form. So now we apply the divergence. Since the new basis is still orthonormal, the divergence of the vector field will be simply sum of partial derivatives. So with respect to the new variables. So we have the partial derivative of u with respect to x prime, double partial derivative, plus double partial derivative of u with respect to y prime. And that's exactly what we wanted to show. So the expression for the Laplacian remains the same when we perform change of variables under the orthogonal transformation like rotation. Let's look at the gradient, divergence, and Laplacian in polar coordinates. So we have some points on the plane, and in addition to the regular orthogonal coordinates x and y, we can measure the distance from the origin, r, and the angle with the horizontal axis, theta. We can, so in addition to the regular, to the Cartesian basis ij, we will also consider unit vectors er and e theta. So er is normal, so er is along the radius direction, so and e theta is the direction tangent to the circle of radius r. Okay, So both ER and E theta have length 1, just like I and J. So on this picture, it becomes obvious that the basis ER E theta is obtained from the basis IJ by rotating the old basis by angles theta. Okay. Now, in addition, we are going to look at the length of the arc that connects the given point, the length of the arc along the circle of radius r from theta equals 0 to our point. Okay, so on this picture, the length of that arc is 5 theta, because the radius of this circle is 5. Okay, but in general, we consider the quantity S equal r theta. Okay, so first observe that the gradient vector, since the coordinate system ER E theta is orthonormal, the gradient vector, gradient of u, has coordinates partial derivative of u in the radial direction plus partial derivative of u in the tangent direction. So that partial derivative in the tangent direction is with respect to the distance covered along the circle, so with respect to S. Okay. Now let's express the partial derivative of u with respect to x in terms of the partial derivative of u with respect to theta. So by the chain rule, since S is r times theta, the partial derivative of u with respect to theta is partial derivative with respect to S times ds d theta. Now ds d theta is simply r, so we get that u theta is r times us. So we get the following identity. So finally, if we replace us in our expression for the gradient by 1 over r u theta, we get the final formula for the gradient in polar coordinates. Now let's convert this expression to the usual Cartesian coordinates. As we mentioned, the new basis ER E theta obtained from the Cartesian basis by rotating by angles theta. So we know the Cartesian coordinates of ER E theta. So the vector ER, so if we take vector I rotated by theta degrees, so we get vector cosine theta, sine theta. And similarly, if you rotate vector j by theta, we get vector minus sine theta, cosine theta. So we have the expression for the gradient in Cartesian coordinates. And the left side, that's just the usual expression of the gradient in Cartesian coordinates. Thus, we immediately get a relation between Cartesian derivatives and derivatives with respect to the polar coordinates. For instance, ux is ur times cosine theta plus 1 over r u theta times minus theta. Now let's compute the Laplacian. So the Laplacian is just the divergence of the gradient, and the gradient is has the orthogonal components ur and us. So you should expect that when you take divergence, it will be urr plus uss. But surprisingly, there is an extra term. It appears because as we move, our coordinate vectors, basis vectors, they are changing the direction. So one way to prove this, this extra term, in the previous slide we discussed the relation between derivatives with respect to polar coordinates and derivatives with respect to x and y. So we can just take take the Laplacian in terms of x, y and recompute the derivatives. But actually that's quite a bit of calculations, and that's what the book have done. Now I'm going to just to explain the intuition behind this extra term. Recall from calculus that we can define divergence as by taking some small region and take integral along the boundary of the normal component of our gradient vector field and divide by the area of the region. So that will be the flux density of the gradient vector field. Now we can take any region we like. It doesn't have to be a circle. In particular, we can take a region which conforms to our coordinate system. So let's take a region like part of annulus sandwiched between two arcs of a circle. So suppose that one arc has radius r, another has radius r plus dr. So this region, it's almost like a rectangle, except that the outside arc is actually longer than inside arc. So inside arc is the radius times the angle, so r d theta. The outside arc, it has longer radius, so there is an extra term, dr times d theta. So when you start computing this integral, since this region is almost rectangle, you are going to get urr plus uss, but you will get an extra term, namely, so you will get 1 over dA times the integral of the normal component of our vector field over this extra length dr d theta. You will get 1 over the area of the region, which is dr times the average of the two arcs. When dr is small, that area is approximately r dr d theta, and that's what goes in the denominator. And times the normal component of the gradient vector field times the extra length, dr d theta. And you see that dr d theta cancels, and the normal component of the gradient field, that's the component in the r direction, so that's just ur. So this is just ur, and we get the results. So this is the informal explanation of what's going on. Now finally, so our expression for the Laplacian contains the second partial derivative with respect to s. S is where s is r times theta. Now recall that the relation between partial derivative with respect to s and with respect to theta. So the double partial derivative with respect to s would be rewritten as 1 over r square double partial derivative with respect to theta. And this is our final expression for the Laplacian in polar coordinates. Now in spherical coordinates, for gradient, we have a similar expression. We'll have two angles here, angle theta with the z-axis and angle phi with the x-axis. When writing the gradient, we'll use a local orthonormal basis which consists of three vectors, one along the radial direction and two along the directions of rotation, rotation along theta and rotation along phi. In the plane formed by the z-axis and our radius vector, r and theta play the role of polar coordinates. So it's not surprising that the first two terms of our gradient look exactly the same as in the polar coordinate. But there is one more degree of freedom, movement in the direction parallel to the xy axis. In the xy plane, phi and r sine theta also play a role of kind of polar coordinates. So this term is not surprising. It's very similar to the second term in polar coordinates. Now, the expression for the Laplacian looks a bit convoluted, but in fact, it has many familiar terms which we've seen in polar coordinates. Namely, we have second partial derivative with respect to r. We have second partial derivative with respect to theta divided by r square. Then we have the familiar term ur over r, except that it's multiplied by 2 this time. But we also have a couple of extra terms. Now, for the complete derivation of this the Strauss, actually, this part is well written in Strauss. One thing is important to notice is that this part, like in many problems, we are looking for functions whose Laplacian is 0, and like in physics, you often have functions with rotational symmetry, which depend on just the distance from the origin. For example, the potential function 1 divided by the distance from the origin. For this function, this complicated, so this entire complicated part becomes 0. So the Laplacian in this case is actually quite simple.